Okay, so today we are looking at Unit 4, Lesson 3, which is where we start to take the ideas from earlier in the unit and apply them to the kind of problems that you're going to see. So your goal again is to find the best or worst or most efficient or smallest or biggest or whatever option of a given situation. And the idea is we use the lesson 2 algorithm. How do you get the extreme value on an interval? And then you just apply it to, whatever situation you might be looking at. Now, the way these ones work, okay, because, for example, if you're trying to create a cylinder, let's just go down to the cylinder question for a sec. It says a pop can in the shape of a cylinder is supposed to be such and such. Like, if I asked you to find the dimensions of a pop can that will use the least amount of material, but I don't specify that the pop can has to have a certain volume, then you would just say it should be infinitely small. It should be 0.1 millimeter wide or whatever. It should be very tiny. The idea with this unit is that you are given some kind of constraint that you need to, make sure is true. And then once that constraint is true, then you find the best possible pop can. So, it's often we're going to be looking at intervals where there's one critical point, which to go back to what we were talking about in the previous lesson, when there's one critical point, we only have to prove that that point is a min or max in order to show that it's an absolute min or max. Remember, if there's more than one point, then you really need to graph. Right? There's not really, you don't really have a good option in that situation. So, what is it we're trying to do here? Number one, we're trying to figure out, in other words, what is it we're optimizing, right? What are we trying to optimize? So that's a good first question to ask. The second thing you need to ask is, what is the constraint? And then you need to use the constraint to make the optimized, let's say, quantity a function in one variable. This is the big point here to understand. If you can get your equation in one variable, you already know how to optimize it. So the idea that we're working on today is, how do I use a constraint equation to turn my optimizing equation into a single variable that I can then do my calculus to. I can take its derivative, find its critical points, and so on. So again, determine the domain of the function. Really, really important. We need to know if we're looking at a closed domain or an open domain and how that might affect the solution that we need to give. We need to use the algorithm, right? And make sure to prove it is an absolute min or max. And then you answer the question. So let's take a look at a simple one first. One that you already know how to do. You probably just haven't thought of it in terms of calculus and optimization before. It says a property owner has 600 meters of fence. She wants to enclose a rectangular field with one side along a wall. Find the dimensions of the rectangular field of maximum area. Okay, so first we should acknowledge that there are many ways to use 600 meters of fence, but only one way to use it, optimally, which is to say the best possible use. Let's imagine that the wall for our our item is here. Okay, I'm going to make a slider for length. We know length can be anywhere from 0 to 600, because you could use up all 600 on length. Width could be anywhere from 0 to 300, because you can't, you have to have two widths, right? So you can't use them up. You can't use all of them up. So let's say one corner of this fence is going to be 0, 0. Another corner is going to be L0. So let's say we start with the idea that L is, 200. Just zoom this out a bit so we can see a bit better. And then what we're going to do is we're going to make a new new point. So C is LW. Why the spacebar thing makes it animate, and then 0W. Okay, so let's say here's a possible fence we could draw, and let's just make a quick here. So the perimeter. Now the perimeter of mine is an L plus 2 W's. Okay, so I'm supposed to use 600 meters of fence. So let's say, for example, I use 300, let's say 400 in the length. Okay, then what I have left to use in the width, they could be 100. Okay, so there you can see I've designed a, box, fence, whatever, that uses 600 meters of fence, and you can see its area here is, for 40,000. Just turn that on as a. Okay, so there it is. Now, if I add, let's say I add another 100 to the length, so now I'm at 500 length. I've used up too much perimeter now, right? So I need to drop the width until it comes down to 600. And you can see that this, setup, as opposed to the one I was just looking at, is less efficient. It only covers 25,000 of area, as opposed to the 50,000 or the 40,000 we had before. So the idea here is to use the following algorithm to kind of solve this. So let's apply it, and then we'll look back at the visual to just help us see what's going on. So number one, we state, what are we optimizing? In this question, it says find the dimensions of a rectangular field with maximum area. So we're doing area. Now area, as you all know, area of a rectangle, length times width. Pretty straightforward, right? Now, this means, right, if you want to find the maximum, okay, so the problem is, right, if we want to find the maximum of this, we have two variables. So if I want to make an area function, do I make it a function area of L or area of width, right? Which one is my input? They're both input. So you have two variables that are trying to input into the same function. You don't have the right kind of function yet. So we go back to the question and we ask, what is the constraint? Now the constraint is another piece of information in the question somewhere that's limiting your area in some way or another. Now the constraint in this question is up above. It's just that we only have 600 meters of fence. This means how this is useful to us is to say that the perimeter, which in our case is length plus 2 width, is limited to 600. Or, well, let's say perimeter equals 600 first. That's our constraint equation. Okay, and that constraint is going to interact with the area equation to allow us to create an equation using only one variable. So now I can go, okay, so I go, what's another way of writing the perimeter here? Perimeter is equal to, there's a single length, I don't need the other length because it's covered by the wall, and there are two widths. So I can say L plus 2W equals 600, and therefore L equals 600 minus 2W, right? Now what I can do with this is I can say create a function of the optimized quantity, which remember is area, in one variable only. And then what we could do is we could say, okay, area function in terms of W is length times width, but we know that length is actually 600 minus 2W, right, times another W. Let's make this just A, just make that a bit clearer. Okay, so here now is the important piece, because once you have this equation, you can now do your calculus and you can just optimize that equation, right? So we can go area in terms of width is 600W minus 2W squared. Therefore, area prime is equal to 600 minus 4W. area prime equals 0, W equals 150. You can see that just 4 times 150 is 600. Okay, so what we just did is we found a point, right, a width value where the rate of change of area is 0, and therefore it is a critical point. Now go back to what you know about optimizing. So find the absolute min or max of the area function. How do you do this? Step 1, find the domain. Step 2, use the appropriate technique. Remember, what is the appropriate technique? Let's just quickly review that. If it's a closed interval, check all critical points and all endpoints. Find out which one's the lowest. If it's an open interval, check to see if there is one critical point, and then check if it's a min or max. Remember, if there is more than one critical point, you have no choice but to graph. Okay, that doesn't come up very often, but if it does, it's not that hard to do. So, what is the domain of our function? Well, if we think about the values for width, right? The values for width that you could have in this equation, so the domain, so let's look at the area of W function. The domain is going to be width is a real number. Let's write it properly. So width belongs to the real numbers, and 0 is the lowest width that makes sense. Really, you could say 0 is less than, because if you have a 0 width, you don't actually have any area at all. And width can be no bigger than 300, because if it's bigger than 300, you're not creating your length has just become negative, remember. So this is it's an example of a question with a closed interval. So closed interval. Therefore, the optimized box is either, or the optimized area is either, right, A of 0, A of 150, or A of 300. Now again, it's obvious that A of 0 and A of 300 are both themselves equal to 0, because in the first case, you've devoted all your fence to the length. In the second case, you've devoted all your fence to the width, and in both cases, you haven't created a lot of area, because it's extremely thin. It's very long, but not very wide, right? So it doesn't capture a lot of area. So 150 is going to be our answer. But just to show it, let's do the second derivative test on A of 150. Actually, no, wait a minute. We don't need to do that. Sorry, we don't need to do a test in this case. A of 0 equals 0. A of 300 equals 0. A of 150 is equal to, let's just go back up and look at this for a sec. So it's 600 minus 2W. So that would be 600 minus 2 times 150 times another 150, which would be 300 times 150, which would be 45,000 meters squared. Okay, and that would be the best fence that you can design in this case. Okay. Now again, I'm trying to go through it slowly and carefully to explain it, but it doesn't actually take that much work when you know how to do it. Let's go back to my diagram for a second, confirm our answer. So I suggested that the length should be 300, the width should be 150. Oops. Okay, so there you could see the perimeter is 600, the area is 45,000. Now let me fix up my drawing a little bit, where I'm going to use the equation that we used, which is that the length is actually 600 minus 2W. So let's go back to here. Let's go back to this point B, and instead of calling this L, let's go 600 minus 2W, so that we can just use W to control everything instead of trying to work with two variables, because two variables, of course, I'm having to adjust both of them. I shouldn't need to do that, right? Our whole point is here, I'm trying to figure out how to do this in one variable. So you can see now, L no longer does anything, right? W controls both dimensions. And you can see that if I make a very long, a very wide fence that's not very long, its area really suffers, right? It's only 2,000. whereas our good one had more like 45,000. When I make width too short, it has the same problem. It's a very low area because it's a very long and thin box. The best box, right? It's like it goes up and up and up towards 45,000, and then it starts to go down, right? And you could see that, where it's going up and then going back down again. We can actually demonstrate this. What I'm going to do here is I'm going to make another point, and we're going to call this point W, and then let's go Q1. Let's say over 1,000, I think should be. So we'll take, basically what I'm going to do here is I'm going to have this point exist. This point represents W, which is the width, and then I've taken the volume, or the area, sorry. I really should call this area. And I just divided it by 1,000, so it's not such a big number. You can see that as I change the value, the area, right, it's very low over here, it's very low over here, and it reaches a maximum, right where we predicted at 150, right? And that point there is sort of the perfect, sorry, my perimeter is all messed up now because it's 2W plus 600 minus 2W. Right, sorry, perimeter's messed up. Perimeter's always going to be 600 the way I've set up the question. But you can see that at 150, you reach this best possible value, right? Where, you just can't do any better than this in this situation. Your area is right at the ideal spot. This corresponds with the equation that we drew. 600 minus 2W times W. Sorry, 600 minus 2x. I've got to use x if I wanted to draw it. Right? It creates a parabola that has its max, like, of course it's really high, so it's a bit difficult to see, but right? It has its max exactly where we said it should at 150. Right? Now again, why don't we use a vertical compression to slow this down so it's not so tall. And you can see that the parabola reaches its maximum right at the value of 150. If I use a 1 over 1,000 vertical stretch, zero key is broken, it'll just create that thing we created before, right? So there's the parabola. You can see it has one critical point. That critical point is a max, although we didn't actually need to check that here because it was a closed interval, so we just checked the endpoints and the critical point. Okay, so again, it's an overkill for this type of question. You could solve this question faster, but it's a really good intro to just the idea of what we're trying to do so that when we come across more difficult questions, we know how to approach them. A piece of cardboard 16 by 30 is to be used to make a rectangular box with an open top. Find the dimensions that will give the box the largest volume. Okay, so first thing to understand about this is that, how does a rectangular piece become an open top box in the first place? Now, I don't think I have a good example of this.